Hi, I'm going to do a quick video explanation of these three homework problems from section 2.1 because they're combining some algebra properties that you know, but sometimes you forget, and the idea of that memory limit that we talked about in limits. So if you understand what's going on just by looking at my steps, that's fine. I'm going to show you problem 33 as well. So if you understand what's going on just by looking at my steps, you could just pause this and study it, and then you don't have to listen to what the heck I'm saying. But if you want my explanation, here it goes. Problem 31, the original problem. The very first thing I do is I try the plug-in, but when I plug in a 0 into the denominator, I get a 0 in the denominator, so I know I have to resort to something else. In this case, it's going to be algebra trickery. And so what I do on that very first step is I factor out a GCF. The GCF is one of the most commonly forgotten factoring techniques in America today. At that point, still if I plug in a 0, I get a 0 in the denominator. Who cares what I get in the numerator? Still big trouble. But what I can do is I can say, you know what? I can pretend the numerator is like sine of x times 1, and I can break this up using an algebra property of this piece over this piece over that piece. It's still the limit of both of those, but by doing that, first of all, I haven't changed anything because sine of x times 1 is sine of x times this thing is still x times that thing. So I've just changed the way it looks, but by doing that, I know the limit as x approaches 0 of that is 1, that's the memory limit, and the limit as x approaches 0 of that, I can plug in the 0 and I get a -1 in the denominator. 1 divided by -1 is -1. So I've really made two limit problems, and if I wanted to, I could have written it like this. Hold up. Oh geez, hold up again. Okay. So this thing I wrote here, I could rewrite it as two limits multiplied by each other, but this is also fine. The bottom line is, by GCF factoring and by rearranging the multiplication to look a little differently, I can get to my final answer of that limit. Now 32 is going to be a little different because now I have a different algebra property I'm going to be using eventually down the line. So I plug in a 0. Who cares about the numerator because the denominator is 0, and that's bad news. But now I'm going to use this algebra property that you used to use back in the day. Say 4x plus 20 divided by 2. The teacher said, hey, you can divide that 2 into both of those and you get 2x plus 10, which is a little bit more pleasing to the eye. So I can divide the x into the first term and the second term to get this. I couldn't do that if these were connected by multiplication. That would be a different algebra property you would need to use. Now that I have this, I can break this into two limits, the limit of the first piece plus the limit of the second piece. And that's the memory limit. This, I plug in a 0 to, oh, there's nothing to plug into, so it stays a 1. Let's take a look at the last one. Okay, I'm going to put this one on here because some people don't like this notation, but sine squared x is the equivalent of writing sine of x squared. It's just a different symbolism technique. Anytime I have sine squared or sine squared, I can rewrite it this way if I feel like it. And the reason that helps me out is I can pretend it's an x times 1 in the denominator and turn this into this, two limits. And remember, I could say the limit is of this times the limit of this if I wanted to write it differently. Memory limit, plug in a 0, this one turns into a 0. 1 times 0 is 0, there's my final answer. All right, I chose these because it is definitely algebra properties that you need to know, but the book mixed them with the memory limit, and altogether it makes for some good limit problems. See ya.